In this video tutorial, we will be differentiating between atoms, elements, and compounds. Alright, let's begin with a brief review of grade 9 science. Well, first off, matter is defined as anything that takes up space and has mass. From there, matter can be split up into two major categories, pure substances and mixtures. With pure substances, they contain only one kind of particle. So for instance, pure oxygen gas only contains oxygen molecules, O2, while pure water only contains water molecules, H2O. Most students have no problems recognizing that this is pure because it's just green dots, there's nothing else in there. So of course it's pure, there's only one thing inside. But how can this be pure when I see pink and black dots? There are two different colors here. How can this be a pure substance? Well, compounds are groupings of atoms that have been chemically combined. So you see how these dots are touching each other? That means they are bonded together. Because they are bonded and stuck to each other, we consider them to be one group. Two pink, one black, two pink, one black, two pink, one black. It is a single particle made up of two pink dots and a black dot. And since each of these particles is identical, two pink, one black, we can consider them to be a pure substance, with only one type of compound present, two pink, one black. So while an element is a substance that is made up of a single type of atom, compounds are also pure substances that are made up of particles that have more than one element. The key here is that it has to have more than one element. So here we have a pink element and a blue element chemically combined, and each of these particles is identical in their makeup, so it's pure. Over here we have a blue and four black elements chemically combined, and each of these particles are identical, so these compounds are pure. Alright, comprehension time. Which circles contain a pure substance? Circles A, B, C, or D? Which circles? Hopefully you chose A, B, and C. So each of these particles is identical, so that's no problem, pure. This one's also pure because every single one of them is identical. So is this one. But this one is a mixture. There are different types of particles inside, so it is not pure. Now, which circles contain a compound? This one was a little tricky. It's just C. This is not considered to be a compound because compounds are made up of more than one type of element, while these two are the same element. So this would be considered to be an element, a pure element, not a pure compound. You need to have different elements chemically combined in order to be considered a compound. And D is a mixture. And of course I gave away the next question, but go ahead and give it a try. If you get this one wrong, I'm going to be very disappointed. Which circles contain a mixture? I really hope you chose D. Now, which circles contain an element? Just A and B. Okay, what I want you to do now is press pause, answer this question, classify each of those circles, A, B, C, D, E, F, G, H, as either being an element, a compound, or a mixture. Press pause. When you're ready, press play, and we'll take it up. Alright, so A is a element. B is a mixture. C is a element. D is also a element. E is a mixture. F is a mixture. G is a compound. And H is a mixture. So, a mixture is made up of two or more pure substances that are mixed together. Now, mixtures can be further divided into homogeneous mixtures and heterogeneous mixtures. Now, a homogeneous mixture is also known as a solution. And these mixtures tend to be difficult to separate. So for instance, in order for you to separate a solution of salt water, where there's salt and water mixed together, you'd have to boil the water away before you're left behind with the sand. You can't just put your fingers in the salt water and pick out the salt particles. It's just not going to happen. It's too small. So homogeneous mixtures tend to be a little more difficult to separate the different parts inside. Furthermore, homogeneous mixtures or solutions have one uniform phase throughout. So when you see the word uniform, you're probably thinking about clothing. So when you go to a store, the employees are all probably wearing the same uniform to help you recognize who works there and who doesn't. So the word uniform in this case just means that they look the same. So homogeneous mixtures or solutions all look uniform. They all look the same throughout the whole thing. It's hard to see the different parts. So salt water, sugar water, it all looks the same throughout. You can't see the salt. You can't see the sugar. I mean, unless it's not been dissolved properly. But if it has been dissolved properly, it all looks the same throughout. To be able to differentiate between salt water and sugar water, you'd have to taste it. They all look the same. Just by looking at it, you wouldn't be able to differentiate. Now, when we use the word solution, most people typically think of liquids. But solutions can also be solids and gases. So for instance, air. Air has many different types of gases inside of it, mostly oxygen and nitrogen. But can you see the oxygen versus the nitrogen? No, they should all be the same. It's uniform throughout. Brass is an example of a solid-solid solution. It is an example of a metal alloy where zinc and copper metals were melted together. So when you look at a brass trumpet, can you tell the different parts are zinc and copper? No, it's all been melted together. It all looks the same. It's uniform. Then there are the ones that we are familiar with. So liquid solutions. So for instance, alcohol and water mixed together to make beer. When you look at a beer, not that you're old enough to have ever seen one up close, of course, it all looks the same. You can't tell the difference between the alcohol molecules and the water molecules. Same thing with solids in liquids. You put powdered salt into water, stir it around, it all looks the same. It's very difficult to see the salt versus the water molecules. So we say that these solutions are homogeneous. They are uniform throughout. Now a solution is made of two components, the solute and the solvent. Usually the solute is what is being dissolved, while the solvent is what does the dissolving. But essentially the part of the solution that's in the smallest amount is called the solute, while the part of the solution in the greatest amount is a solvent. So in salt water, you should have more water than salt. If you have more salt than water, then it's not a solution, it's just wet salt at that point. Now a heterogeneous mixture, on the other hand, is made up of two or more substances that can more easily be separated. Furthermore, we can usually tell just by looking at it that it's made up of more than one substance. So for instance, salt and pepper. If you mix these two together, I can see the white salt and the blackish brownish flakes of pepper. I can tell that it's not pure and that there are different stuff inside of it. Oil and water. Because they don't mix well, oil usually floats on top of the water, I can see the two different components, and just by looking at it, know that it's not a pure substance, that there are two different components to it. So, let's classify each of these three as either being homogeneous, all looking the same, or heterogeneous. You can see the different components. So granite is heterogeneous. I can see the different types of minerals inside of it. It is definitely not pure. Human blood is a little more difficult. It is actually heterogeneous. You can see the different parts of it. Now, when you bleed or when you see blood, you're probably not looking close enough to see the different parts. But if you look under a microscope, you can definitely see that there are red blood cells, plasma, fat, proteins, lipids, etc., etc. There are so many different things in blood, it does not look pure under a microscope. Meanwhile, when you dissolve copper 2 sulfate with water, it all looks the same. Even if you put this under a microscope, it would all look the same. It's so small, the difference is, it looks uniform throughout. You can't tell the difference between the copper 2 sulfate particles and the water that dissolved them. So, putting this all together, everything we've just discussed is summarized in this big giant chart. Matter can be divided into heterogeneous mixtures or homogeneous mixtures. Heterogeneous mixtures are more easily separated, and it's obviously a mixture. We can tell the difference between the different parts. Whereas a homogeneous mixture is uniform throughout. You can't tell apart the different components, nor is it easy to separate them. But if you can separate them by physical means, like boiling them apart, then we call that a homogeneous mixture. If you can't separate them by physical means, then at that point it's a pure substance, of which they can be separated into elements, just one single type of atom, or compounds, several different types of atoms chemically combined together into one pure particle. Alright, what I'd like you to do at this point is identify each of these boxes as being A, element, B, compound, C, a mixture of elements, D, a mixture of compounds, or E, a mixture of elements and compounds. So remember, if the two circles are touching, then that means they are chemically combined and they are one particle. Alright, so press pause. When you're ready, press play, and we'll take it up together. And here are your answers. Most of them should be pretty straightforward. However, maybe 12 might have given you some trouble because they look very, very similar, but it's actually 2 black, 1 white versus 2 white, 1 black. So there are 2 different compounds there. Same thing with this one, 4 black, 2 whites versus 4 whites, 2 blacks. So there are 2 different compounds there. This one is definitely different, and this one's also definitely different as well. So this should be a review from grade 9, how to count atoms. Let's briefly review over some of the rules you would have learned. First, the symbol of an element represents one atom of the element. So there's no need to put a 1 there. This is automatically assumed to be one atom of sodium. On the other hand, a subscript is a number written in the lower right-hand corner behind the symbol of an element. If there's more than one atom of the element, then a subscript is used to indicate the number of atoms present. So here we have 2 atoms of hydrogen. Now if you have a subscript outside a bracket, it multiplies all the elements inside the bracket. So this bracketed area shows that these groupings of atoms are stuck together. We call this a phosphate ion. So there are 2 of these phosphate ions, these PO4s. So when you look at that, 1p, 2p, altogether 2 phosphorus. 4 plus 4, altogether 8 oxygen. Or if you'd like, just multiply the 2 into the bracket. So 2 times 1 equals to 2 phosphorus. 2 times 4 equals to 8 oxygens. And of course, there's only 3 magnesiums. While these smaller numbers are called subscripts, the bigger numbers in front of the element is called a coefficient. Alright, so this number is in front of the chemical symbol and indicates the number of atoms of that element. So we have 3 atoms of carbon. But more importantly to us, a coefficient also multiplies the number of atoms of each element in the entire formula. So over here, so this is saying we have 2 water molecules, H2O, H2O. While this one's saying we have 3 copper 2 sulfates, so 3 of these CuSO4s. Now a lot of students have difficulty recognizing what the difference is between a subscript and a coefficient. So when you look at these 2 scenarios, they both seem to tell you the same thing. 2 hydrogens, 2 oxygens. Well, this 2 multiplies everything in the back, so that's 2 times H, 2 hydrogens, 2 times O, 2 oxygens. So what's the difference? Well, H2O2 says I have 1 molecule of H2O2. They're all chemically combined together into one giant molecule. While 2HO says that I have 2 of these hydroxide ions, so the HO and the HO. Some of you might still be confused, so let me draw you a picture that might make more sense to you. Saying 2HO is like saying I have 2 Big Macs, while 1 H2O2 is like saying I have 1 McHeart Attack. In both cases, you have the same number of ingredients, 4 buns, 4 buns, 4 patties, and 2 of those inner buns, and whatever they're called. But same number of ingredients. Same thing, same number of atoms, 2 H's, 2 H's, 2 O's, 2 O's, but the subscripts and coefficients tell you a different story of how they are assembled. So subscripts tell you how to make your molecule. So how do you assemble this monstrosity? While coefficients tell you how many of these molecules to create. So how many of these burgers will you create? Alright, so subscripts tell you how to assemble it, coefficients tell you how many to create. So going back here, I recommend you ignore the coefficient first and just count how many atoms are in each of these molecules. In this case, there are 2 hydrogens and 1 oxygen. But since you want to make 2 of these water molecules, you want to multiply your recipe by 2, and now you have 4 hydrogens and 2 oxygens. Now I know some of you think you can do it all in one step, and you probably could, absolutely, for the easier ones. But for the more complicated ones, like you'll see on the other page, even I will still ignore the coefficient first, calculate how many there are in just one molecule, and then multiply by the coefficient afterwards. It's better to do it in 2 steps, take a little extra time, be a little more careful, and then you're less likely to make a silly mistake. I personally would prefer to take an extra 2 seconds to guarantee my mark than to save that extra 2 seconds and then lose it in a silly mistake. Alright, so I have 1 copper, 1 sulfur, and 4 oxygens in this compound. But since I want to make 3 of these, I'm going to multiply everything by 3, giving me 3 coppers, 3 sulfurs, and 12 oxygens in the end. Again, I'm going to ignore the coefficient. I have 1 lead. Now, there's a bracket over here, So there's 2 of these NO3s, so I'm going to multiply it in. Means I have got 2 nitrogens and 6 oxygens. But now I want to make 4 of these, so I'm going to multiply everything times 4, giving me 4 leads, 8 nitrogens, and 24 oxygens. So what I'd like you to do now is press pause, try this out yourself. When you're ready, press play, and we'll take it up together. Alright, and here are your answers. The only ones that you might have difficulty with is over here. You'll notice that the hydrogens were split up into 2 different areas, H4 here and H3 here. You must combine them together to make 7 H's. Now there is a reason why they separate these H's, is because this is a polyatomic ion and this is a different polyatomic ion, but you'll learn more about that one in grade 11. You might also need some help with these ones over here. So what I've done again was calculate just by itself without the coefficient, 1 barium, 2 chlorines, then realize I need to make 3 of these barium chlorides, so I multiply everything by 3, and that's what I've got. Alright, so this one over here says I have 2 atoms, types of atoms anyway, 1 barium type and 1 chlorine type, so there's 2 types altogether, but I have 9 atoms altogether because 3 of them are bariums, 6 are chlorines, add them up, you get a 9. I did the same thing down here. First I calculate how many aluminum atoms by itself without the coefficient, same with the carbon and the oxygen. There are 3 types of atoms, aluminum, carbon, oxygen. Then there are 4 aluminum carbonates that I want to make altogether, so I multiply everything by 4, giving you these values with a total number of atoms of 56. Finally down here, exact same thing. There are 4 types of atoms, nitrogen, hydrogen, chromium, oxygen. Then I calculate it by itself, how many of each type there were. Since I'm making 2 of these compounds altogether, multiply everything by 2, get these final values as well.